Welcome to this DVD on electrochemistry. This is part 1 of 2. Just a gentle reminder before we start. All our DVDs, this one included, are protected under the New Zealand copyright law, and as such it is illegal to copy them. It doesn't matter where in the world you are. Now before we commence, please make sure you have a pen, pencil and notepad ready. I urge you to take as many notes as what you deem are necessary. I specifically urge you to take down all the steps for the various methods that we will be covering later on, all definitions and anything else that you feel is really important and crucial to your understanding. Now, when it comes to the examples, I would like for you to first watch how I work through them and carefully listen to my explanations, then rewind and attempt them on your own. But when it comes to the exercises, please work through those on your own first. Don't fast forward ahead. It doesn't matter how tempted you may be to do so. And then you can listen to my explanations, we can compare answers, and you will have a really good idea of how you fared. Now remember, you are in charge of the remote. You can pause, skip, fast forward, rewind as many times as what you want. So make good use of it. The purpose of this DVD is also for you to learn as you go, and I'm going to help you to do that by frequently repeating really important terms and definitions. This will save you a lot of time during your homework sessions, as well as help you to prepare for those exams coming up later on. It will also enable you to more confidently use these terms and definitions, and that's important. So let's make a start. So many reactions that take place on this planet involve the transfer of electrons from one substance to another. Combustion reactions is an example of such transfer of electrons between elements and/or compounds. Exchanges of electrons between substances give us oxidation-reduction reactions, which is what we will be studying in this course. Every time you use your laptop, digital camera or calculator, oxidation-reduction reactions occur. That is because batteries work by redox reactions involving the transfer of electrons. All biochemical energy reactions, such as photosynthesis and respiration, depend on redox chemistry. You may recall that photosynthesis is the process by which green plants convert carbon dioxide and water into carbohydrates in the presence of sunlight. Carbon dioxide is reduced to a carbohydrate and water is oxidized into oxygen. Right now, as you are watching me, oxidation-reduction reactions are taking place in your body, enabling you to understand and follow what I am saying. You see, in living cells, glucose is oxidized to carbon dioxide and water in the presence of oxygen, and energy is released. This energy is then used by the body for doing physical and mental work. So you see, oxidation-reduction reactions play a very big role in keeping our bodies going. But oxidation has also been blamed for aging, cancer, hardening of the arteries and rheumatoid arthritis. And that is why many people take antioxidants such as ascorbic acid, vitamin C, or vitamin E. Oxidation-reduction reactions are also responsible for food spoilage. The next time you have some leftover pizza after movie night and you forget about it for 2 days, have a look at that pizza and you will see oxidation-reduction reactions have taken place. It is spoiled. Or an apple going brown. The main source of oxidation is oxygen from the air. Preservatives that are added to foods are often reducing agents. The natural ability of algae and other water plants to oxidize harmful materials in sewage has been used in sewage ponds or lagoons, also known as oxidation pond systems. The operation of a car battery, the rusting of metals, the process involved in photography, The way living systems produce and utilize energy are but a few examples of a very common and important type of chemical reaction, the oxidation reduction reaction, or redox reaction for short. Now, the aim of this DVD is to enable you to describe oxidation reduction, or commonly called redox processes, apply oxidation reduction or redox principles, and to discuss oxidation reduction processes. Now, let's have a look at the learning outcomes. By the end of this DVD, you should be able to define the terms oxidation and reduction. Define the terms oxidizing agent, also called an oxidant, reducing agent or reductant, and use them correctly. Now, these are some of the terms I'll be repeating a lot. Identify the oxidant and reductant from an equation. Link explanations of oxidants and reductants to the correct species, very important. Distinguish between spectator ions and reactant species. You should also be able to recognize oxidation and reduction reactions in terms of the addition and removal of oxygen, the addition and removal of hydrogen, electron transfer, as well as the oxidation number. Discuss and explain oxidation and reduction processes in terms of electron transfer and oxidation number increase or decrease. Determine oxidation numbers, or oxidation states as they are also called, of unknown atoms in formulae using oxidation number rules. Distinguish between oxidation numbers and ionic charge, and state the colors of common oxidants and reductants. You should furthermore be able to describe and interpret expected observations, write and use correct formulae, write balanced oxidation and reduction half equations, write completed and balanced oxidation reduction reactions for acidic medium and basic medium. You should also be able to recognize and discuss the ability of halogens to act as oxidants in reactions with other halides and water. Now, before commencing with this DVD, it is very important that you know the appearance and states of aggregation of the common oxidants and reductants, and their products are required. These will be provided in tables a little bit further on. Because these are so important, I will be dotting them throughout the DVD. So I still want you to pay attention and learn as many of them as what you can, even although I will be giving you some that you will only be required to know in the following year or maybe even at university. It makes it more interesting, and it is really important. For instance, if I give you HCl, you are not going to know if I'm talking about hydrogen chloride or hydrochloric acid unless I put in brackets AQ for aqueous or G for gas. So it's very important in order to duplicate experiments clearly. Now, the states of aggregation are solids, liquids and gases. So we are going to be putting an S in brackets when we're referring to a solid, an L in a bracket when we are referring to a liquid, and we use G for gas. Now, we use the abbreviation AQ for an aqueous solution just to describe a substance dissolved in water. So that's really what it means. For instance, in the example I mentioned to you just now, we will write HCl with gas G in brackets just behind it for hydrogen chloride. But when we are talking about an aqueous solution, hydrochloric acid, which is what you commonly use in the laboratory, we will be putting an AQ for aqueous just behind HCl. Throughout this DVD, IUPAC spelling will be used. Now, IUPAC stands for International Union of Pure and Applied Chemistry. and this union has a set of agreed upon rules for the naming of substances. And hence the element with atomic number 16 on the periodic table will be spelled as sulfur with an F and not as sulfur, which is how we would spell it if we were, for instance, in New Zealand or in England. Please remember to be consistent with your spelling. So for instance, the ions derived from sulfur will be spelled sulfide, sulfate, and sulfite, etc., and not as sulfide. Oxidation reduction, or redox reactions for short, involve the transfer of electrons from one reactant to another. It is an electron transfer reaction, and it is very, very important that you remember that from the start. So a redox reaction is an electron transfer reaction. Now we say that while one substance is being reduced, another substance is being oxidized. In other words, they both happen at the same time and they both have to happen. So the term redox is used for the simultaneous processes of reduction and oxidation. So here's my first question to you already. Can you have an oxidation reduction reaction when only reduction happens? No, you need them both, reduction and oxidation. Now, oxidation of a reactant always involves the loss of electrons. It can also involve the gain of oxygen and or the loss of hydrogen, but not necessarily so. So you are safe sticking with electron transfer. Now, reduction of a reactant always involves the gain of electrons. It can also involve the loss of oxygen, which is what people originally focused on when discovering oxidation reduction reactions. It can also involve the gain of hydrogen. Now, the mnemonic oil rig reminds us that oxidation is loss of electrons. So we have oxidation is loss. Please learn that now. Reduction is gain of electrons. Reduction is gain, which gives us reg. Please learn that now as well. Let us now have a look at an example of an electron transfer reaction. So when an iron nail is placed into a blue solution of copper sulfate, the nail becomes coated with a reddish tinge of solid copper metal. Now I'm going to demonstrate that to you, but first of all, let us write a molecular equation and then an ionic equation for this reaction. So this is what our molecular equation would look like. So what is a molecular equation? A molecular equation is one in which substances, such as these substances, are written as if they are molecular, where in actual fact they are ionic. Now this equation describes what you are actually doing in a laboratory. However, this molecular equation that you see does not describe what is actually happening at the level of molecules and ions. For that purpose, we need to write an ionic equation. So let's do that now. Here you can see that we have written the copper as copper 2+. So that would be the ion. Over here, we would have copper 2+ and we have our sulfate ion. And here, of course, here we've got the ferrous ion, Fe2+. The sulfate ions present in the copper sulfate solution are not shown in the ionic equation because they do not take part in that reaction. They are called spectator ions. So let us now have a look to see what happens when an iron nail, a nail made of iron, reacts with a copper sulfate solution, which is an aqueous solution. Let's see what happens. So here I have an iron nail, and I'm going to place this iron nail into this blue copper sulfate solution. and just leave it there for a few seconds. Now I know that the sulfate ions in that blue copper sulfate solution are not going to partake. Those are the spectator ions. So what products am I expecting? I'm expecting solid copper to form. So that copper should coat my nail if everything goes well, and then the other product would be ferrous ions. Those are also called the Fe2+ ions. So here you can see this part over here is our original iron. That was not in contact with a copper sulfate solution. And at the bottom here, we have that solid copper that formed, that coated our iron nail. And this is a perfect example of a redox or oxidation reduction reaction. It is due to God's logic and His natural laws that elements such as iron, molecules, and ions react in a predictable and consistent way no matter where on Earth. For instance, we can take this iron and dunk it into a copper sulfate solution, and it doesn't matter where we are, whatever our geographic location, and it is still going to react in the same way to give us copper, as well as ferrous ions. So whether you are in America, England, Africa, New Zealand, iron will always react with copper sulfate in exactly the same way. So let's now have a closer look at our ionic equation to see exactly what happened. So here we have our ionic equation. And we can see that iron, the iron metal, lost 2 electrons to form the ferrous ion. Copper, on the other hand, gained 2 electrons to form the element copper, solid copper. So which is the oxidized species and which is the reduced species? You remember the mnemonic I told you earlier on about oil reg. Oxidation is loss and reduction is gain. So where do we have a loss of electrons? We have that with the iron. So the species that is oxidized is the iron. But remember, we can't have oxidation without reduction. So we definitely have a reduced species. So which one would that be? The copper 2+ ion is the reduced species. But now where did the 2 electrons lost by the iron metal go to?